Greetings. So, till now we have looked upon the case for the case of heat generation when there is uniform rate of heat generation inside the body, specifically the plane wall, and both the sides of the plane wall are maintained at uh, by are maintained at different temperature by the different fluids, means left side as well as the right side. But in the next case, which we are going to look now, um, in this case, the both side of the plane wall are maintained at the same temperature. Okay, so if this wall and this wall are maintained at some particular temperature, let's say Ts, it's also Ts. This is possible only when the rate of heat transfer from this surface and from this surface are same. And this is also possible when there is same fluid on both the sides with the same heat transfer coefficient, okay, and free stream temperature on both sides. So same temperature, free stream temperature, and same heat transfer coefficient on both sides. Only then the both surfaces of the plane wall can be at the same temperature. But as heat is generated inside the body, and due to symmetry, the maximum temperature for this case will be at the center. Okay, for the case of uniform rate of volumetric heat generation, right? So due to symmetry, maximum temperature will be at the center. Due to symmetry, right? So now we will derive the temperature distribution and we will try to prove it. So what will be the maximum temperature and its location? Okay, so let's start with the same heat conduction equation in the Cartesian coordinates, and mind it that we are considering our reference location at the center plane, not at the left side plane, because it is symmetrical body, right? Okay, so we are taking it for convenience. So let's derive. So starting with this one-dimensional heat conduction equation, del square T by del x square plus Qg by K equal to 1 by alpha del T by del T. Alright, since it is steady state heat transfer, so it will be 0. Okay, and since it is one dimensional also, so we can write this as ordinary derivative, as we have seen this up till now, the previous lecture also. So integrating is twice, we can get the temperature profile. So dt by dx equal to minus Qgx by K. K is thermal conductivity of the material of the wall, plus arbitrary constant C1. Since the maximum temperature is at the center, the slope at the center will be 0 for the temperature. So first boundary condition is, due to symmetry, at x equal to 0, it means center, the slope is 0. So we can find the C1 value. So Qg times 0 by K, slope is 0, right, plus C1. So C1 is 0. Next, integrate this equation again, so we can get temperature as minus Qg x square by 2 K plus C2, right? And at x next boundary condition is at x equal to L by 2 or minus L by 2, the same temperature is there, T is equal to Ts, right? So put that surface temperature T will become surface temperature, mind it, this is a function of x. So T at x equal to L by 2, which is Ts is nothing but T at x equal to plus L by 2 or minus L by 2, same value of temperature, right? So Qg plus minus Qg into L square by 4 divided by 2K plus C2. So we can have C2 as Ts plus Qg L square by 8K, right? So put that in this equation. Let's call this equation number 2. So we can have the temperature profile like minus Qg x square by 2K minus Qg x square by 2K plus C2. C2 is this Ts bar plus Qg square, Qgl square divided by 8K. So we can write further by rearranging T minus Ts equal to Qg by 2K L square by 4 minus x square. If we take out the L square common and L square by 4 common, so we can have Qg L square divided by 8K times 1 minus x by L whole square times 4. This will be the temperature profile, and we can further write like this. This is nothing but T of x minus Ts. So, but we don't know this surface temperature because we know only H and T infinity on both the sides. So we have to find Ts by some means, right? So finding T1, we have to apply energy balance on the wall. The same thing we did in the last class also, right? Consider the control volume around it and apply the energy balance. Rate of heat entering plus rate of heat generation minus rate of heat going out of the system. Energy balance equal to rate of heat stored, right? This is 0 because it is steady state. Right, and there is no heat coming inside. Whatever heat is generating inside, that is going out. Maximum temperature is inside the body. Since maximum temperature is inside the body, so heat will be going out, no heat will be coming in, right? So that's why on both sides we have same fluid HT infinity, both sides surface temperature Ts, right? So whatever heat is going on the right hand side, same heat will be going on the left hand side. So whatever heat is generating, it will be going out according to the energy balance, and the heat that is going out we can write that Q left hand side plus Q dot right hand side, and heat generation is Qg volumetric rate times the volume of the body. If it is non-uniform heat generation, we have to, if the rate of heat generation is a function of XYZ coordinate system, then we have to integrate that over the whole surface, over the whole body, right? But since it is constant, we have uniform rate of heat generation, it means Qg is constant, so we can write, we can take Qg out of this integration and write this, right? And same heat is transferring from the left hand side and right hand side, so from Ts to T infinity 2 times, so H times A times Ts minus T infinity plus H times A times Ts minus T infinity. So we can have surface temperature from here as Ts minus T infinity. Volume is nothing but cross sectional area of the wall times L. This is nothing but the length, right? Cross sectional area is A. Ts minus T infinity, A will be cancelled out, so we can have Qg L by 2H. So now we have H known, T infinity known, Qg L are known, so we can find Ts. So we have boiled down the Ts into knowns, right? So if we know Ts, we can find T at any x from our equation. Let me write that. Sorry. Qgl square divided by 8k times 1 minus x by L whole square times 4. So we can put Ts here and we can find T at any location. And if you want to find the maximum temperature will be at x equal to 0. So you have to put 0 in this equation, so you can find maximum temperature as Qg L square divided by 8k. This term will become 1 because this term will go to 0, right? So we can find T at x equal to 0, which is nothing but T maximum equal to Ts plus Qg L square divided by 8k, and Ts is this, right? So in the next lecture we will see about the heat generation case for solid cylinder and solid sphere, when surface temperature is maintained constant. Thank you.